This video is going to be about integrating using partial fraction decomposition. So when you have an integral that has a rational function, which is one polynomial function divided by another, like the one that we have here, the first thing that you want to try to do is long division. If the degree of the numerator is higher than the degree of the denominator. In this example, the degree of the numerator is third degree and the degree of the denominator is fourth degree, so we do not need to do the long division. The next thing that we would want to look at is, can we factor the denominator? If we can factor the denominator, then we want to go ahead and do that. So factoring x to the fourth plus 9x squared will involve factoring out a common factor of x squared. And we will have left over x squared plus 9. So x squared is basically a repeated linear factor as far as partial fraction decomposition is concerned. X squared seems to be a second degree or a quadratic factor, but it can be broken down into x times x. Now, x squared plus 9 is a quadratic binomial factor, and it cannot be factored anymore. X squared plus 9 is an irreducible quadratic factor. So we have a repeated linear factor with x squared and an irreducible quadratic factor. So we take our integrand and we are going to write that down. And we are going to set it equal to three fractions, 1, 2, and 3. Now, the first fraction, I am going to put my irreducible quadratic factor. And so when you have a quadratic factor, an irreducible quadratic factor in the denominator, you have to put a linear factor in the numerator. And that linear factor has to be of the form some constant x plus another constant. It could be ax plus b, bx plus c. It could be rx plus t. It could be mx plus w. It doesn't matter. Then in the next fraction, I am going to put the first power of my linear factor. And then we want to put a constant above that. Whenever you have a linear factor in the denominator, you are going to be putting a constant in the numerator. So as far as my constants go, let's just go in alphabetical order. We have an A, a B, so now I'm going to put a C. Again, whatever you call the constants, it doesn't matter. I just like to go in alphabetical order. And then because this is a repeated linear factor, we have to put the x squared here with a constant in the numerator. Now, if this was an x cubed, then we would have to add another term with an e over the x cubed term. So every power up to the power of the repeated linear factor. The next thing that we do is we multiply both sides of this equation. We have an equation here now, right? Very complicated looking equation. We multiply both sides by the least common denominator. Well, the least common denominator is always going to be this denominator, x to the fourth plus 9x squared. So we multiply both sides by that, but I'm going to write it in its factored form over here. And of course, we're going to be writing that over here. I don't have room, so I'll just write LCD. Well, on the left-hand side, this cancels with itself. So we're left with 9x cubed plus 7x squared plus 36x plus 27. And on the right-hand side, This x squared plus 9 term cancels with this x squared plus 9 term, leaving me with the x squared factor times the ax plus b. X squared times the ax plus b. Then, when we multiply the second term by the least common denominator, the factor of x cancels with one of these two factors of x's, leaving us with one factor of x times x squared plus 9 to be multiplied by the numerator. So we will have cx times x squared plus 9. And then the third fraction gets multiplied by the least common denominator. The x squared terms cancel out completely, leaving us with d times x squared plus 9. The next step on the left-hand side, we don't really need to do anything on the left-hand side. Just bring that on down. On the right-hand side, we need to clean this up by multiplying all of this through. So x squared times ax will be ax cubed. X squared times b will be bx squared. Cx times x squared is cx cubed. Cx times 9 is 9cx. D times x squared and d times 9. Next thing that we want to do is what is referred to as equating coefficients. On the left-hand side, we have a coefficient of 9x cubed. So I'm going to write down 9x cubed. And then on the right-hand side, I'm going to look for all of the terms that have an x cubed in them. So we have ax cubed plus cx cubed. Then we have 7x squared. And so the x squared terms would be here, bx squared, and dx squared right there. The third term, 36x. And then my x terms here would be the 9cx, and that's the only one. And then finally, we have a 27 as our constant term, and the constant term is 9d. And I like to make little marks underneath everything so I know everything has been accounted for. So this is called equating coefficients. So let's think about this. If this term on the left-hand side is going to be equal to this expression on the right-hand side, then the cubic terms must be equal, the squared terms must be equal, the linear terms must be equal, and the constants must be equal. Well, what we're going to do then is solve for a, b, c, and d. In this particular case, it's not going to be too bad because right here, we have 27 is equal to 9d, or d is simply equal to 3. Then we have, what we're going to do then with the rest of these is we're going to get rid of the variables. So I'm just going to take out the x cubes here. So I have 9 is equal to a plus c. Then here I have 7 is equal to b plus d. And then 36 is equal to 9c. Well, now we can kind of solve a little bit more. We already know that d is equal to 3. Now we can see that c is going to be equal to 4. It's just solving 36 equals 9c. And then, let's see. Here we have an a and a c. So if I was to take, well, I can't do, oh yeah, C is 4. So if C is 4, we have 9 is equal to A plus 4, or A is going to be equal to 5. And then finally, we have 7 equals B plus D. We know that D is equal to 3. So 7 is equal to B plus 3. So B is equal to 4. All right. So we have our values of A, B, C, and D. They are 5, 4, 4, and 3. So on the next slide, I'm going to have to jump back and forth here a little bit. We're going to have the integral. And remember, we had 3 fractions. We had 1, 2, 3 fractions. In the bottom of the first one, we had ax plus b. No, I'm sorry. We had, in the bottom of the first one, we had x squared plus 9. Let me get rid of that. All right, so we had x squared plus 9. And then we had x here and x squared. Our coefficients were 5, x plus 4. Let's go back to, so we had ax plus b over x squared plus 9. A is 5, b is 4. So I'm going to substitute those in here. And then I'll put c over x, which is also 4. And then d over x squared, which was 3. So we're going to have 4 over x and 3 over x squared. And those are all positive, so I can just make those pluses. And so here is the integral that we want to integrate. Now, let's break this up into separate integration problems. Sometimes it's easier to look at the integration problem in pieces. So we have the integral of 5x plus 4 over x squared plus 9 dx plus the integral, and I'll put the 4 out here, dx over x plus 3 times the integral of 1 over x squared dx. All right. Now, the last two aren't going to be too difficult to integrate because this is simply a du over u problem. And this one we can just use the power rule on. But before I do that, I want to take a look at this because right now we still don't know how to integrate this. We can't do a u substitution on it. If we let u be equal to the denominator, then du would be 2x, and we have something x plus 4. So what we can do is we can actually break this into 2 separate integrals itself. We can take the 5x and divide it by x squared plus 9 dx. And then we can take the 4. And again, I'm going to put the 4 out in front. So what we have is dx over x squared plus 9 plus my 4 times the integral of dx over x plus 3. And I'm going to write this as the integral of x to the negative 2 dx. Now, the first one here is a u substitution problem. U is equal to x squared plus 9. So du dx is going to be equal to 2x. So dx is equal to du over 2x. This one is an arctangent problem. And so the antiderivative of arctangent, the formula for arctangent is we have a du over a u squared plus a squared. then that is going to be equal to 1 over a times the arctan of u over a. And in this particular case, u is simply equal to x, and a is going to be equal to 3. So, integrating all of these, then we are going to have I'm just trying to see if I can fit this down here or go on to another slide. All right, so we're going to have the integral here of, we have, so when we put it, we have 5x, and in the denominator we have u, and then we have du over 2x. So the x's cancel out. We're going to be left with a 5/2 times the integral of du over u, right? Which then will become 5/2 times the log of u. So on the next slide, let's kind of put this together here. So we have the integral um, 5/2 the integral of du over u. The next one was 4 times dx over plus 4 times dx over x squared plus 9. Then the next one was 4 over dx over x. And then the last one was 3 times the integral, I believe it was x to the negative 2. All right, so this then becomes 5/2 times the log of u. This then is going to become, according to the formula on the other side, we're going to have the 4 divided by a, which is 3, times the arctan of x over 3. And this is going to be the log rule. This is 4 times the log of the absolute value of x. And this is going to be, we have 3 times x to the negative 1 divided by negative 1. So that's x to the negative 1 divided by negative 1. Over here, u, let's go back and see what was u again there. U was x squared plus 9. So we have 5/2 the log of x squared plus 9. And notice we don't need to put that in absolute value because x squared is always going to be positive, plus 9 will always be positive, plus 4/3 arctan of x over 3 plus 4 times the natural log of the absolute value of x. And so what's this is? This is going to be minus 3 over x plus c. And that should about do it. That would be our final antiderivative, or integrating that problem using partial fraction decomposition. All right, so I hope that was somewhat helpful. See you in class.